composite numbers. I have a feeling I might have to do 2 videos, so we'll see what happens. What is a prime number? Well, a prime number is a number that is divisible by exactly 2 numbers, 1 and itself. Let me rephrase that. A prime number is a number divisible by exactly 2 different numbers, namely 1 in itself. And I bring that up because 1 is not prime, all right? A composite number is a number that has more factors. And this word here, factors, is important. It's actually what it means to be... my daughter might help me. A composite number is a number that has more factors, that has more than 2 factors. And I'm going to use that word factors in a minute. So let's take a quick look at the first few numbers that we know. Oops, pardon me. So like I said, we're not going to start with 1 because 1 is not divisible by 2 numbers. It's divisible by 1 and itself, but 1 is itself. So here's the problem. 2, the only numbers that multiply to 2 are 2 and 1. So 2 is prime. 3 is 3 and 1. 4 is 4 and 1, but it could also be 2 and 2. And you can see how I'm writing this. If I'm making these factor trees, or as they're called in elementary school. Phoebe, what do you call these? When you have something like this, what's this called? A number what? Good one. It's a number bond, but these are different types. These are product bonds, all right? These are number bonds with products. This is called a factor tree, and you can see that the factors of 4 are 1, 2, and 2.
Actually, 2 plus 1 is 3.
Yes, I know that 2 plus 1 is 3. This is for a little bit older kids. So 5 would be 1 and 5. 5 is prime. 6 is 2 times 3. So 6 is not prime. 7 is 1 times 7. So 7 is prime. 8 is kind of neat. It's 4 times 2. But then 8 can be written as 2 times 2 times 2. 9 can be written as 3 times 3. And then 10 can be written as 2 times 5. So between the numbers of 2 and 10, the prime numbers are 2, 3, 5, 7. Now, a lot of people will say, oh, look, it should be 2, 3, 5, 7, 9. But no, once again, 9 is not prime, all right? 9 is composite because it has the factors of 3. The other thing you might notice, as you go on, 11 is prime, 13 is prime, 17 is prime, 19 is prime, 23 is prime, 29 is prime, etc., etc. You might notice that they're all odd except for 2. And that's because, well, why do you think? It has something to do with even numbers. All even numbers are divisible by 2. So, Phoebe, you're very clever. So, yes, all even numbers are divisible by 2. So, therefore, if you have an even number, it can be divided by 2, which makes it not prime, except for the one exception, which is 2. All right. So, I'm going to look at something called the greatest common factor, all right? So, the greatest common factor. And the greatest common factor is actually kind of neat because a lot of people learn about the greatest common factor, but they don't really know why they're learning about it. So, let's see what that means. If I have a number like 36, and I said, well, what are the numbers that go into 36? I might say, well, 4 times 9, and then say 2 times 2, and 3 times 3. All right, and let's say I had the number 45. What numbers go into 45? I know it's 5 times 9. Oh, by the way, it'd be 2 times 2 times 3 times 3 equals 36. 4 times 9 is 36. 2 times 2 is 4. 3 times 3 is 9. So therefore, 2 times 2 times 3 times 3 equals 36. 45 I can write as 5 times 9. 5 is prime, but 9 is not. So 45 can be written as 3 times 3, which is 9, times 5. So now look at this. If I wanted to find the greatest common factor of 36 and 45, it would be 2 times 2 times 3 times 3 over 3 times 3 times 5. What do they have in common? And it looks like they have 3 times 3. So the greatest common factor of those two is 9. Now you might say, why is that useful? Well, it's useful because look, what's 9 divided by 9? It's just 1. So if I want to divide this, 36 and 45 is a fraction, but if I divide it, it becomes 4 out of 5. That's simplest form. All right? Finding the simplest form is actually very useful for many different reasons. Let's see. Oh, I'm sorry. I'm just checking on my time here. So I'm going to go back to here. And I was looking at the Goldbach Conjecture, and we will get to that. So if I want to do something like 18 and let's say 27, once again, I'd say, all right, well, I know that 18 can be written as 2 times 9, and that's 3 times 3, and then 27 is 3 times 9, and that's 3 times 3. So 18 is really 2 times 3 times 3. 2 times 3 is 6, times 3 is 18. 27 is really 3 times 3 times 3. Their greatest common factor is 9. Which means if I want to simplify this, I would just divide 9 by 9 and get 1. Alright. What about the least common multiple? Now, once again, the least common multiple might not be something that's high up on your radar, but I am going to show you something that's kind of neat about it. If I had something such as 3 over 20 plus 5 over 15. Well, if you want to find the least common multiple, and you do that because you want to add these fractions, I would look at 20. I'd say, oh, 20 is really 2 times 10, 4 times 5, 2 times 2. So let's say it's really 20 is really 2 times 2 times 2. That's not right. Oh, I made a mistake. I'm glad I caught that. 20 is really 2 times 2 times 5. 15 is really 3 times 5. Well, you can see that these are not the same. I'm looking for the least common multiple. So I want to make 20 and 15 the same. Right now, the only thing they have in common is a 5 times 5. So in order to make them the same, I need to make sure that everything that 15 has, 20 has, and everything that 20 has, 15 has. So 15 has a 3, but 20 does not. So I'm going to multiply that by a 3. So now they both have a 3. 20 has 2 more 2's. 2 times 2. So now look. Now they are all the same. What is 2 times 2 times 3 times 5? Well, I know that 2 times 5 is 10. I know that 3 times 2 is 6. So the least common multiple of 15 and 20 is 60. Alright? 6 times 10 is 60. And then once I know that, I can say, oh, I would just multiply this by 3 over 3. And multiply this by 4 over 4. And because look what we did here. This one ended up with that, and this one ended up needing that. That's where these 3's came from, and that's where these 4 came from. So I would end up with 9 over 60 plus 20 over 60, and then you could add these up and get 29 60ths. Alright. I am running dangerously close to running out of time, but I think I can get this last part in. It's a little bit of a challenge for you. I want you to give this a try. There was a man named Goldbach, and he had a conjecture. A conjecture is something that isn't proven, but appears to be true, but nobody can prove it. And he said that every even number greater than 2. So that would be 4, 6, 8, 10, 12, 14, etc., can be expressed as the sum of two prime numbers. So 4 could be 2 plus 2. 6 can be 3 plus 3 because 2 and 3 are prime. 8 could be 3 plus 5. 10 could be 5 plus 5. 12 could be 5 plus 7. 14 could be 3 plus 11. So once you know your primes, and like I said, I'll list some of them here. 5, 7, 11, 13, 17, 19, 21, 23, 29, 31, 37, etc., you can give the Goldbach Conjecture a try. See how many even numbers that you can make using the product, or not the product, the sum, adding of two prime numbers. And that's it.